Hello everyone, and welcome to today's presentation. I'm excited to share with you an overview of coroutine context and its essential components in Kotlin coroutines. The title of our session is Coroutine Context and its Essential Components. During this talk, we'll explore how coroutine context defines the behavior of a coroutine through key elements like job, dispatcher, coroutine name, and coroutine exception handler. Let's dive in and see how these pieces work together to make coroutines powerful and manageable. So, when thinking about implementing a retry mechanism in a coroutine, there are a couple of effective approaches we can consider. One straightforward method is using the repeat function. This allows us to attempt an operation multiple times, like trying to fetch data up to 3 times. If an exception occurs during fetch data, we catch it and then introduce a delay, say, 1 second before trying again. Another, more flexible approach is creating a custom retry with exponential backoff. This means that if a request fails, we wait for an increasing amount of time before the next attempt, which helps reduce the load on the server and increases the chances of success over time. The key point here is that these mechanisms help make our network calls or operations more resilient. They handle intermittent failures gracefully, which is especially important in real-world applications where network issues are common. By understanding and applying these retry strategies, we're reinforcing the overall theme of building robust, fault-tolerant asynchronous code in Kotlin coroutines. Let's take a closer look at the difference between yield and delay in Kotlin coroutines. First, yield allows a coroutine to voluntarily give up its thread and let other coroutines run. It's important to note that it doesn't delay the coroutine itself. Instead, it suspends it momentarily, giving other coroutines a chance to execute. This is useful when you want to be cooperative and ensure that multiple coroutines share resources fairly. On the other hand, delay suspends the coroutine for a specific amount of time, effectively pausing it without blocking the thread. This is handy when you need to wait for a certain period, like waiting for a timer or delaying repeated actions. In the example here, we launch a coroutine that calls yield, which gives other coroutines a chance to run before it continues. After that, it prints a message showing how yield cooperates with other coroutines without blocking. Understanding this distinction helps us write more efficient and cooperative asynchronous code, fitting into the broader theme of managing concurrency smoothly in Kotlin. So let's talk about how coroutines can really boost your app's performance on Android. Essentially, they allow us to run background tasks, like I/O operations or network requests, without blocking the main thread. This is a game changer because when the main thread is free, your app stays responsive and smooth. You see, when the main thread gets blocked, it often leads to ANRs, those pesky, app not responding dialogues, which we definitely want to avoid. By using coroutines, we can handle intensive tasks seamlessly in the background, making the user experience much better. Overall, this approach helps create faster, more efficient apps that feel snappy and responsive, aligning perfectly with our goal of delivering high-performance Android applications. Can you share state between coroutines safely? The answer is yes, but it requires some careful strategies. Sharing mutable state directly can lead to race conditions and data inconsistencies, so we need to manage access properly. One common approach is using a mutex, which acts like a lock. Only one coroutine can acquire it at a time. This ensures that critical sections, where shared data is accessed or changed, are executed exclusively, preventing conflicts and keeping our data consistent. Another useful tool is stateflow or shared flow from Kotlin's coroutines. These are designed for sharing state or events in a thread-safe way. They're considered hot flows, meaning they keep emitting data even if there are no collectors, and all subscribers receive updates in a controlled manner. This simplifies synchronization because it handles the complexities internally, ensuring everyone sees a consistent view of the data. Finally, there's the actor model, which is a different approach altogether. Instead of sharing state directly, actors communicate via message passing. An actor encapsulates its own mutable state and processes messages sequentially within its own coroutine. This pattern guarantees that only the actor itself can access or modify its state, removing the need for explicit locks and making concurrent state management safer and more straightforward. Connecting all these ideas, the key takeaway is that managing shared state in coroutines requires careful strategies, whether through locking mechanisms like mutex, reactive streams like stateflow, or the actor model. Each method helps us maintain data integrity and avoid race conditions, which is crucial when building reliable, concurrent applications. So let's dive into what run blocking test and run blocking actually are and how they differ. Both of these are coroutine builders, but they serve quite different purposes, especially when it comes to managing time and testing. Starting with run blocking test, this one is part of the Kotlin Coroutines test library. Its main purpose is to help us write unit tests for time-dependent coroutines. What makes it special is that it uses a virtual clock instead of real time. This means that delay, calls, or timeouts happen instantly, allowing tests to run extremely fast and deterministically. You don't have to wait for actual delays, which makes your testing process much more efficient. On the other hand, run blocking is a core coroutine builder that's used in regular code. It launches a new coroutine and blocks the current thread until everything inside that coroutine completes. It works with real-world time, so if your code calls delay, the thread actually pauses for that duration. This is useful when you need to bridge non-suspending code with suspending functions, like during startup or setup in apps. But it's important to remember that using run blocking in production, especially on Android, can block the UI thread and cause performance issues, so it's generally better suited for testing or scripting. To sum up, run blocking test is optimized for testing scenarios, fast, deterministic, and virtual time, while run blocking is more suitable for bridging code in actual applications, but with caution to avoid blocking the UI unnecessarily. Understanding these differences helps us write better, more efficient coroutine code, especially when testing complex time-dependent logic. So, how do we handle multiple asynchronous operations efficiently in Kotlin? The key is to use async along with await. What this does is, you start multiple coroutines in parallel by wrapping each operation with async. For example, you can fetch the user and the profile at the same time by launching 2 async blocks. Then, when you need the results, you call await on each of those deferred objects. This way, you're not blocking, but rather running tasks concurrently, which saves time and improves performance. Remember, the most important concept here is that async starts the operation immediately, and await is used to retrieve the result once it's ready. This pattern really ties into our overall theme of efficient, non-blocking asynchronous programming in Kotlin. So let's talk about what an actor is in the context of Kotlin coroutines and channels. Essentially, an actor is a coroutine that receives messages one after another through a channel. This means it processes messages sequentially, which is really useful for managing state safely. One of the key benefits here is that it enforces single-threaded access to mutable state, helping us avoid common concurrency issues like race conditions. For example, in the code snippet, we create an actor called counter, which maintains a total. It listens for messages on its channel, and each time it receives a message, it adds that message to the total. This approach is powerful because it encapsulates state within the actor, ensuring that only this coroutine modifies the state, which simplifies reasoning about concurrent operations. It ties back to our overall theme of managing asynchronous tasks safely and efficiently with Kotlin coroutines. All right, let's dive into coroutine start options. First up, we have default, which means the coroutine starts immediately as soon as you launch it. This is the most common choice when you want your coroutine to run without delay. Next is lazy, which is quite interesting. It won't start until you explicitly call start or join on the job. This gives you more control over when the coroutine begins. Moving on to atomic, this option makes sure the coroutine can't be canceled before it actually starts running. It's useful when you want to guarantee that the task will run once triggered. Lastly, we have UNDISPETCGD, which starts immediately in the current thread and continues until it hits its first suspension point. This can be handy when you want the coroutine to start right away, but still allow suspension later on. To illustrate, if you write launch, start equals coroutine start. Lazy, the coroutine won't run until you call job start or job join. Understanding these options helps you control the execution flow of your coroutines more precisely, which ties into our overall theme of efficient asynchronous programming. So let's take a closer look at how coroutine cancellation actually works under the hood. Essentially, cancellation in coroutines is a cooperative process. This means that the coroutine itself needs to actively check whether it has been canceled. The most common way to do this is by checking the isActive property. If isActive is false, it indicates that the coroutine has been canceled, and it should stop what it's doing. It's also important to note that most suspending functions like delay or with timeout inherently support cancellation. When you call these functions, they periodically check for cancellation and respond accordingly, allowing your coroutine to terminate gracefully. However, if you block a thread intentionally using thread sleep, or perform heavy computations without any checks, cancellation won't be effective. In such cases, the coroutine won't notice that it has been canceled because it's stuck in a blocking or intensive task. To handle this properly, you'd need to explicitly check isActive during these operations. This highlights the importance of writing cooperative code, making sure your coroutines check for cancellation at appropriate points. This way, your application remains responsive and can cancel tasks cleanly, maintaining overall robustness in your asynchronous workflows.